Possibly the most explosive idea ever to have blown the mind. Parasite, then for the doctor to intervene and bring the temperature down might be the worst thing he could do. He might actually be scuppering a natural adaptation to make life difficult for the parasite. There is a certain amount of evidence that this is at least sometimes the case. It's difficult to do experiments on the temperature of mammals like us because, of course, our temperature is very carefully regulated, and if you try to increase the temperature artificially, you don't succeed. So a scientist called Kluger, Matthew Kluger, did an interesting experiment using lizards. And the point about lizards is that they don't regulate their temperature in the way we do. They regulate their temperature by behavioral means. When a lizard needs to be heated up, or indeed any reptile needs to heat up, what it does is it gets itself into a warm place. In the case of these lizards, they put themselves into the sun. So a lizard is quite effective at regulating its temperature, not by the way we do it, but by moving into the sun when it's cold and moving into the shade when it's hot. Kluger reasoned that if a high temperature, a fever, is an adaptation by the host to make life difficult for a parasite, an infected lizard should deliberately seek out a higher than normal temperature by moving into the sun. So what he did was he injected into lizards a bacterium, infected them with this bacterium, and the lizards then moved into the sun, which had the effect of raising their temperature. He then did the experiment of forcing infected lizards to stay in the shade, didn't give them the opportunity to move into the sun, and sure enough, the infections became more severe. So at least in these lizards, where it was possible to do experiments, Kluger was able to demonstrate that the lizard equivalent of a fever, which means getting into the sun, does indeed have a beneficial effect by making life hard for bacteria. A rather remarkable finding, which was given a Nobel Prize in 1927. Nowadays it's slightly horrifying. Wagner Jahregg was working on syphilis, and he noticed that patients with syphilis tended to get better if they happened to catch malaria. And he guessed that it might be that the high fever, the high temperature that malaria gives you was having the effect of killing the bacteria that give syphilis, that makes syphilis. And so he actually got some thousands of patients with syphilis and deliberately infected them with malaria. And sure enough, this cured them of syphilis. He was in fact given the Nobel Prize for this. Nowadays you would use antibiotics, but it's a good illustration of this effect that high temperature, high fever might actually be a Darwinian adaptation to get rid of parasites. On the other hand, it's also possible that a high fever is an adaptation by the pathogen to improve its own living conditions in the body and to speed up its own reproduction rate. So we have two opposite theories. Darwinian medicine doesn't give the answer. Darwinian medicine sets up the questions that should be answered by doctors. Well, I hope that's given a brief idea of how Darwinian medicine might work. And there are various other aspects of Darwinian medicine. For example, thinking about the fact that we have an evolutionary history. Many people, probably many in this room, suffer from lower back pain. The human frame seems to be very vulnerable to lower back pain. And it's a plausible idea that the reason for this is that we've rather recently evolved from four-footed creatures where the natural gait is walking on all fours. And within the last few million years, we have risen up onto our hind legs, and we're now walking around in a very unnatural way for the mammal skeleton. And so, not surprisingly, there are side effects of this, and back pain may be one of them. Well, I now want to talk a bit about Darwinism itself before returning to medical considerations. Darwin himself dramatized the power of selection, natural selection, by the analogy of artificial selection. The slide shows a wolf with two of its descendants, a dachshund and what's that? Is it a chihuahua? I think it's a chihuahua. And that just shows what can be achieved by selection in a relatively short time, I mean, a matter of a few thousand years. If you wanted to demonstrate Darwinian selection experimentally, what would you do? You would take a wild animal like a wolf, systematically set about administering a selection regime, turning it into, say, a dachshund. That's not quite what happened, but you can see the power of selection to do that. In nature, of course, it isn't done like that. It isn't actually humans that do the selecting, it's nature that does the selecting, it's the survival of the fittest. But the principle is exactly the same. Here's another artificial demonstration of the power of selection. This is with fruit flies, Drosophila, being artificially selected for their tendency to approach or go away from light. That happens to be a very easy thing to automate the selection of. You just generation after generation breed from those fruit flies that like to approach light. That's the upper line, the yellow line. Or in a different selection line, you breed from those who avoid going towards the light. And you find in a very few generations, that figure shows up to 20 generations, you find a complete separation between these two lines of fruit flies. Well, that's what you can achieve in 20 generations. In fruit flies, each generation takes about a fortnight. In bacteria, each generation takes only a matter of minutes. 20 bacterial generations could pass in a single day, which shows what we're up against when we're struggling against evolving creatures, evolving parasites like bacteria. During the few days that you are suffering from some disease, the pathogens inside you, the bacteria or viruses, whatever they are, could be evolving through the same number of generations as you see there on the graph for fruit flies. This is why, of course, we're all advised when we're given a course of antibiotics that we must finish the course. Don't just go on until you feel better and then stop. The reason is immediately clear to anybody who understands Darwinian natural selection. But doctors, even today, seem to fight shy of using Darwinian language for this case, although it's an absolute type specimen of a Darwinian selection. In my own GP's waiting room, I picked up a pamphlet warning patients that they must, of the dangers of antibiotic resistance, warning patients they must complete the course. But it never once said in the pamphlet that this is because of Darwinian natural selection. Instead it said, bacteria are clever. They learn to cope with antibiotics. Well, as a professional in the field of public understanding of science, I wonder, why did somebody think that the public would understand bacterial resistance better if it was phrased as being clever and learning, rather than simply telling them the truth. This is natural selection. I mean, presumably the thinking was that learning is something we all do and understand, whereas natural selection is not normally taught at school. But it's actually deeply unhelpful because people will be genuinely and rightly puzzled at the suggestion that bacteria are clever. Any fool knows bacteria aren't clever. It would be far more illuminating if that pamphlet had said bacteria are naturally selected so fast that they can actually evolve resistance to antibiotics during a few days. It's a striking, vivid demonstration of the power of natural selection. There's another artificial selection experiment. This time it's with rats, selecting for tooth quality, measured as time in days to develop tooth decay in a certain regime. And the blue line is rats that were selected to be resistant to tooth decay. And you can see that in, again, a matter of about 20 generations, you have a dramatic improvement in the ability to resist tooth decay. Which raises questions is that already may have occurred to you. If it's possible to take rats who begin with a rather high susceptibility to tooth decay and within a mere 20 generations breed such a dramatic improvement in resistance to tooth decay, why didn't it happen already? Why didn't it happen in nature? Why were those rats hovering down there at this low tooth quality rate? If it's possible for them to get better under an artificial selection regime, why didn't it happen before? Interesting question. I can think of two possible answers. One would be that these were laboratory rats whose ancestors had been feather-bedded for a large number of generations, under which conditions they didn't have to survive because they were looked after in the laboratory, well-fed, well-watered. It was rather difficult to die young. And so quality of rat, quality of tooth, might have indeed gone down. If